Hello 10th class students. As many of you will be opting for MPC group or a BIPC group in near future, and many of you will be writing the different competitive exams. So here I am going to extend the topic of periodic classification of elements to the next level. So these videos are related to that part. Okay, they are again related to concepts only, based on the concepts, just a little bit of extension of the topics which you have to go through once. Okay, so go through these videos very carefully, try to understand the maximum concepts which are available in this particular videos. Thank you.
In the previous videos, we've talked about only the first ionization energy. In this video, we're going to compare the first and the second ionization energies, and we're going to use lithium as our example. So in the previous video, we already know that lithium has an atomic number of 3, so there are 3 protons in the nucleus. And a neutral atom of lithium, the number of electrons equals the number of protons. And so we know there are 3 electrons in lithium here. The electron configuration is 1s2, 2s1. So we have 2 electrons in the 1s orbital. So we can go ahead and put those 2 electrons in the 1s orbital like that. And then we have one more electron, and that electron is going to go into the 2s orbital like this. And so that would be a very simple picture of the neutral lithium atom. If we apply enough energy, right, we can actually pull away this outer electron here. So we can pull away that electron, and we call this the first ionization energy. So the first ionization energy, and to pull away that electron takes approximately 520 kilojoules per mole. And so once we've pulled that electron away, right, we no longer have a neutral lithium atom, right? We would have a lithium ion because we would still have 3 positive charges in the nucleus, but we have only 2 negative charges now. We only have 2 electrons because we pulled one away. So 3 minus 2 gives us plus 1. So this is the lithium plus 1 cation, and the electron configuration would just be 1s2 because we lost the electron in the 2s orbital. And so we could keep going. We could apply some more energy and pull away another electron. So let's say that we pull away this electron this time. Okay, so we're taking a second electron away, and so we wouldn't call this ionization energy 1, we would therefore call this ionization energy 2, because this is to take away the second electron. And this value turns out to be approximately 7,298 kilojoules per mole. And so if we take away that second electron, right, once again we still have 3 positive charges in the nucleus, but we have only 1 negative charge now, so only 1 electron. So this is no longer the lithium plus 1 cation, this is a lithium plus 2 cation, because 3 minus 1 is plus 2. So this is lithium plus 2 here. And the electron configuration would be only 1 electron in a 1s orbital, so 1s1. And so we can see that there's a big difference between the first ionization energy and the second ionization energy. So 520 versus 7,298. So let's see if we can explain the reasoning for this extremely large difference in ionization energies. And we're going to use the 3 factors that we've talked about in the previous videos, right? So the first factor we discussed was nuclear charge, which refers to the number of protons in the nucleus. Right, so if we look at the neutral lithium atom, right, 3 positive charges in the nucleus, that positive charge is what's going to attract this electron in magenta here. Right, and if we look at the lithium plus 1 cation, similar situation, right? We still have a 3 protons in the nucleus, and that positive charge is what's going to be attracting this electron as well. And so because of the same number of protons, we have to think more about effective nuclear charge as opposed to how many protons there are in the nucleus. And before we do that, we have to consider the effect of electron shielding. So let's talk about electron shielding next. So electron shielding, also called electron screening. So electron shielding / screening. All right, so when we think about electron shielding, we're thinking about the inner orbital electrons here. So going back to the neutral lithium atom, right, these 2 inner shell electrons right here are going to repel this outer shell electron, right? So this one is going to repel this one as well. And so you could think about it as they screen the electron in magenta from feeling the full force of the positive 3 charge in the nucleus, because electrons repel other electrons. And so the way to calculate the effective nuclear charge, right? So we've done this in the previous videos as well. The simple way of calculating effective nuclear charge is to take the number of protons, right? So plus 3. And from that, you subtract the number of shielding electrons. So in this case, it would be these two electrons in the 1s orbital. So 3 minus 2 gives us an effective nuclear charge of plus 1. And so the electron in magenta isn't feeling a nuclear charge of plus 3. It's really only feeling an effective nuclear charge close to positive 1, because the actual value is approximately 1.3 when you do the more complicated calculations. And so the effect of electron shielding is to decrease the overall nuclear charge that this electron magenta feels. And so when we move over here to this electron, right? So we're talking about this electron in magenta for the lithium plus 1 cation, there really isn't the same it's not the same situation, right? There's not much electron shielding. This electron over here might repel it a little bit, right? But there are no inner shell electrons repelling this electron in magenta. And because of that, right, the electron in magenta is going to feel this positive 3 charge, much more of the full positive 3 charge of the nucleus. And so therefore there's going to be a much greater attractive force holding this electron in magenta to this nucleus, and therefore you'd have to apply more energy to pull that electron away. So the effect of electron shielding tells you, right, the second electron is much harder to remove than the first, and so we see a large increase in ionization energy from the first ionization energy to the second ionization energy. The last factor that we discussed was distance, right? So the distance of those electrons in magenta from the nucleus, right? So on the left, once again going back to the neutral lithium atom, this electron is in the second energy level, right? So it's further away than this electron, right? This electron is in the first energy level, in the 1s2. So this distance here is smaller than the distance on the left. And so since the distance is smaller, right, this electron in magenta feels more of an attractive force from the nucleus, right? Once again, that's Coulomb's law. And so therefore, there's an increased attractive force. Therefore, you take more energy to pull that electron away. So it takes much more energy to pull the second electron away than the first. And so that's why we see an increase in ionization energy. So distance says the fact that this electron is closer means it takes more energy to pull it away. And that's another reason why this number for the second ionization energy is so much larger than the first. So it takes a heck of a lot more energy to pull away your second electron. And that explains why we see lithium forming a plus 1 cation, right? Because it doesn't take anywhere near as much energy to pull away one electron as it does to take away 2 to form a lithium 2+. And so this is one way to tell what kind of an ion will form. Look at the ionization energies, and when you see a huge jump, right? When you see a huge jump, that clues you in as to which ions are easier to form.
What I want to do in this video is discuss what it means to be a metal or metallic nature. So first, let's just think about the metals that we encounter in everyday life, or based on our experience, the things that we associate with being a metal. So the elements that really jump out at us at metals, or we always refer to, hey, that's a metal or that's metallic, are things like iron, or nickel, or copper, or silver, or gold, or aluminum, or at least for me, these are the ones that immediately pop out as, hey, these are I've seen these things before, and they all feel like metals to me. But now let's think about what's true about these things, and as we'll see, many other elements on the periodic table that give them this metallic nature. What do we associate with having a metallic nature? Well, one is that these things can be shiny. These things tend to be shiny, that there's kind of a gloss when light shines on it. They're not just kind of a matte color. They look metallic, literally. That's sometimes the word that's used for it. It has a metallic shininess to it. Another thing that we associate with it is that they tend to be fairly dense. If I take a block of a metal, and if I drop it into water, I imagine that sinking, that it's not floating on top of the water. We also imagine them having a very high melting point, that they tend to be solid at room temperature. Solid at room room temperature. And as we'll see, this is true of all metals except for one of them, which is mercury, which is shiny, but at room temperature, as you might be familiar, is in its liquid form. Now, the other things that I associate with a metal is that I can make things out of them I can bend them and shape them in different ways. If I think of aluminum foil, I can bend it. It's not just going to crack. I can bend it and put it into different shapes. Even things like iron, it might take a lot of pressure to do it, but they're bendable, they're malleable. And definitely, things like gold and silver and copper, you can actually mold into different types of jewelry. If you put pressure on it, it's more likely to bend than crack and just kind of shear off. So let's put malleability. They're malleable. Malleable. And then the other thing that I associate with metals is that they conduct electricity well. Conduct electricity. A place that you'll see metal in your life is if you open up your electronics, you'll see wires that might be made out of copper, or you might have components that are made out of other metals like gold or silver or whatever else. So given that these are some of the properties that we associate with metals, let's think about what's happening at the atomic level to give these elements these properties. The way I think about it, let's just go with copper for a second. Let's just imagine a block of copper at the atomic level. So let's say this is one copper nucleus right over there, and it has its sea of electrons. It has its sea of electrons. Just like, or not sea of electrons, it has all of its electrons in the various orbitals. We'll talk about sea of electrons in a second, but this is kind of its cloud of electrons, I should say. So this is electron cloud. So the electrons are just jumping around in this cloud. It's really a probability density, or there's kind of a certain probability that could be at any point in that cloud. And so let's imagine a big solid piece of copper. So you would have a bunch of these. You would have a bunch of these all together, all forming the solid. And what allows metals to be malleable, to do things like conduct electrons, conduct electricity, which is the movement of electrons, is essentially for them that they're very willing to share electrons with each other. By sharing electrons, so you can imagine this is one copper atom, that's another. Let's say they're sharing some electrons. That's what allows the electricity, or this flow of electrons, to happen. If these electrons are loosely bound, then if you put a potential difference, a voltage, let's say that you put a potential difference so that this side is more negative and that this side is more positive, then the electrons are going to want to get away from the negative charge, move towards the positive charge. And if they're relatively freely bound, they can kind of move from one cloud to the next. And you kind of end up having what's often called a sea of electrons. Let me write that down. You have a sea of electrons, which would make this conductive. And that's why you see so much wire made out of copper. And the sea of electrons is also what makes it malleable. If someone on this side would have put a lot of pressure this way, and on that side put a lot of pressure that way, things that are rigid would just kind of crack and break, right? Would just break right over there. But because you have the sea of electrons, it allows it to be malleable. This part might just bend down a little bit, that part might bend up, but the metallic bond is not going to break. And so given that this metallic nature really comes from the willingness of these atoms to share electrons with each other, to create the sea of electrons, I encourage you to pause this video and think about which atoms on the periodic table, which elements are more likely to do that, to share electrons with others and with each other. And really this is the same principle that we thought about ionization energy and electronegativity. So pause the video. So I'm assuming you've had a go at it. So which elements are most likely to share electrons? Well, we've already seen that if we're on the left side of the periodic table of elements, group 1, for example, they only have one valence electron. It would be very hard for them to get enough electrons to complete that outer shell. And if they get rid of that one valence electron, they can go to a more stable state. So they really want to give away electrons. And the ones over here, they're so close. If we talk about the halogens, they're one electron away from completing their outer shell. They're greedy. They want to hog these electrons. They tend to be electronegative. The noble gases, they're done. They definitely don't want to share electrons with anyone. They're kind of in a very stable state. Now, the other thing that we've talked about is as we go down a group, our atoms are getting larger and larger and larger. So the outermost, that 55th electron in cesium, is much more loosely bound because it's further away than the, say, the third electron in lithium. So just as we saw as the elements in this bottom left have a very low ionization energy. It doesn't take much energy to remove an electron from them. These are the ones that are most likely to share electrons, and these actually have the highest metallic nature. So high metallic nature. And the ones on the top right, these are going to be the opposite. They're very unlikely to share electrons. They're very electronegative. They have a very high ionization energy. They have a low metallic nature. So I can imagine some things are popping into your brain at this point. You know, we started thinking of the elements that in our everyday life we associate with metals. But what I'm saying is that these things over here have an even higher metallic nature. But what about something like calcium? You know, every day when I typically, or when a lot of people imagine calcium, they think of kind of a white, chalky substance, very rigid, not very malleable, not very good, not very shiny, not very good at conducting electricity. Based on what I just told you, this would have a higher metallic nature than something like aluminum. And what you have to remind yourself is that what you see is not actually pure calcium. That kind of chalky thing, that's calcium carbonate. Pure calcium, actually, this is actually a picture of pure calcium. And it is shiny. It does have these metallic properties. So the general trend here is that all of this is very high metallic nature, and these are very low metallic nature, which also makes you probably realize, wow, most of the periodic table is a metal of some form. If aluminum is a metal and all of these things have a higher metallic nature, then all of this stuff are metals, and that is the case. The S block, the D block, the F block, these are all metals, and then a good chunk of the P block are considered metals, and then these are kind of sometimes referred to as metalloids, and then this section of the periodic table is not considered a metal, and that makes sense. The noble gases, they are gases. They are not very reactive. They don't bond, so they don't form kind of a structure that can even do this type of thing. And these other ones over here, even carbon, when it formed a lattice, it does not conduct electricity well. It's not so. It tends to not be so malleable. If you think about something like a diamond, or if you think about, well, a diamond might be the best example of that. So anyway, hopefully this gives you a sense of metallic nature and the trends in the periodic table. High metallic nature, and as you go to the top right, lower and lower metallic nature.
Before we get into electron affinity, let's really quickly review ionization energy. And let's start with a neutral lithium atom with an electron configuration of 1s2, 2s1. A lithium atom has 3 protons in the nucleus, so a positive 3 charge. 2 electrons in the 1s orbital, so here are the 2 electrons in the 1s orbital, or our core electrons, and 1 electron in a 2s orbital. This is our outermost electron, our valence electron. The valence electron is shielded from the full positive 3 charge of the nucleus by the presence of the core electrons. So like charges repel, and these core electrons repel this outer electron and shield it from the full positive 3 charge. But there still is an attractive force between the positively charged nucleus and this outermost electron. So opposite charges attract, and our outermost electron still feels a pull from the nucleus. Therefore, since the outer electron is attracted to the nucleus, it takes energy to completely pull away this valence electron from the neutral atom. So if we pull away that outermost electron, we lose our valence electron and we're left with a lithium ion with a positive charge. Positive 1 charge because we still have 3 protons, but only 2 electrons now, so overall a +1 charge. Since this ionization takes energy to rip away the electron, the ionization energy is positive and it's measured in kilojoules per mole. Let's compare that with electron affinity. So in electron affinity, let's say we're starting with our neutral lithium atom again, but this time, instead of taking an electron away, we are adding an electron. So we would add an electron to the 2s orbital. So we started off with 3 electrons in the neutral lithium atom, and we're adding one more. So the electron configuration for the lithium ion would be 1s2, 2s2. So still 3 positive charges in the nucleus, 2 electrons in the 1s orbital, but now we've added an electron, so we have 4 electrons total, 2 in the 2s orbital. So let me highlight the electron that we added in magenta. So this is the electron that we added to a neutral lithium atom. And this electron, we know, is shielded from the full positive 3 charge of the nucleus by our 2 core electrons in here, right? So like charges repel. It's also going to be repelled a little bit by this electron that's also in the 2s orbital. So this electron is going to repel this one as well. But there is an attractive force between our positively charged nucleus and our negative charge on the electron. So this electron that we added still feels an attractive force that's pulling on it from the nucleus. And so if you add this 4th electron, energy is given off. And since energy is given off, this is going to have a negative value for the electron affinity. For adding an electron to a neutral lithium atom, it turns out to be negative 60 kilojoules per mole. So energy is released when an electron is added. And that is because the electron that we added is still able to be attracted to the charged nucleus. So if the nucleus has an attraction for the added electron, you're going to get a negative value for the electron affinity, or that's one way to measure electron affinity. Note that the lithium anion is larger than the neutral lithium atom. It's just hard to represent it here with those diagrams. So as long as the added electron feels an attractive force from the nucleus, energy is given off. Let's look at one more comparison between ionization energy and electron affinity. In ionization energy, since the outer electron here is attracted to the nucleus, we have to work hard to pull that electron away. It takes energy for us to rip away that electron. And since it takes us energy, we have to do work, and the energy is positive in terms of ionization energy. But for electron affinity, since the electron that we're adding is attracted to the positive charge of the nucleus, we don't have to force this. We don't have to do any work. Energy is given off in this process, and that's why it's a negative value for the electron affinity. Electron affinities don't have to be negative. For some atoms, there's actually no attraction for an extra electron. Let's take neon, for example. Neon has an electron configuration of 1s2, 2s2, and 2p6. So there's a total of 2 plus 2 plus 6, or 10 electrons, and a positive 10 charge in the nucleus for a neutral neon atom. So let's say this is our nucleus here with a positive 10 charge, 10 protons, and then we have our 10 electrons here surrounding our nucleus. So this is our neutral neon atom. If we try to add an electron, so here let's add an electron, so we still have our 10 protons in the nucleus, we still have our 10 electrons, which would now be our core electrons. To add a new electron, this would be the neon anion here. So 1s2, 2s2, 2p6, we filled the second energy level. To add an electron, we must go to a new energy level. So it would be the third energy level, it would be an s orbital, and there'd be 1 electron in that orbital. So here is, let's say this is the electron that we just added. So we have to try to add an electron to our neon atom. But if you think about the effective nuclear charge that this electron in magenta feels, right? So the effective nuclear charge, that's equal to the atomic number, or the number of protons, and from that you subtract the number of shielding electrons. Since we have 10 protons in the nucleus, this would be 10, and our shielding electrons would be 10 as well. So those 10 electrons shield this added electron from the full positive charge from the full positive 10 charge of the nucleus. And for a quick calculation, this tells us that the effective nuclear charge is 0. And this is, simplifying things a little bit, but you can think about this outer electron that we tried to add of not having any attraction for the nucleus. These 10 electrons shield it completely from the positive 10 charge. And since there's no attraction for this electron, energy is not given off in this process. Actually, it would take energy to force an electron onto neon. So if we wrote something out here, if we said, all right, I'm trying to add an electron to neon to turn it into an anion. Instead of giving off energy, this process would take energy. So we would have to try to force this to occur. So it takes energy to force an electron on a neutral atom of neon. And we say that neon has no affinity for an electron. So it's unreactive, it's a noble gas, and this is one way to explain why noble gases are unreactive. This anion that we intended isn't going to stay around for long, so it takes energy to force this onto our neutral neon atom. So you could say that the electron affinity is positive here, it takes energy, but usually you don't see positive values for electron affinity for this sort of situation. At least most textbooks I've looked at would just say the electron affinity of neon is 0, since I believe it is hard to measure the actual value of this. Here we have the elements in the second period on the periodic table, and let's look at their electron affinities. We've already seen that adding an electron to a neutral atom of lithium gives off 60 kilojoules per mole. Next we have beryllium with a 0 value for the electron affinity. That means it actually takes energy, so this number is actually positive, and it takes energy to add an electron to a neutral atom of beryllium. So if we think about going from a neutral atom of beryllium to form the beryllium anion, when we look at electron configurations, neutral atom of beryllium is 1s2, 2s2, and so to form the negatively charged beryllium anion, it would be 1s2, 2s2, and to add the extra electron, it must go into a 2p orbital, which is of higher energy. And so this is actually the same thing, or very similar to neon, which we just discussed. For neon, the electron configuration was 1s2, 2s2, 2p6, and to add an extra electron, we had to go to the third energy level. We had to open up a new shell, and the electron that we added was effectively screened from the full nuclear charge by these other electrons. And a similar thing happens here for the beryllium anion. To add this extra electron, we have to open up a higher energy p orbital. This electron is on average further away from the nucleus and is effectively shielded from the full positive charge of the nucleus, and therefore there's no affinity for this added electron. So there's no affinity for this electron, so it takes energy to form the beryllium anion, and that's why we see this 0 value here for beryllium. Beryllium has no value for electron affinity, or it's actually a very positive value, and we just say it has a 0 value. Next, let's look at boron here. So this gives off negative 27 kilojoules per mole. And we can see a little bit of a trend here as we go from boron to carbon to oxygen to fluorine. So as we go across the period on the periodic table, more energy is given off, and therefore fluorine has the most affinity for an electron. So as we go across a period, we get an increase in the electron affinity. So the negative sign just means that energy is given off, so we're really just looking at the magnitude. More energy is given off when you add an electron to a neutral atom of fluorine than if you add an electron to a neutral atom of oxygen. And we can explain this general trend in terms of effective nuclear charge. As we go across our period, we also have an increase in the effective nuclear charge. And if the added electron is feeling more of a pull from the nucleus, which is what we mean here by increased effective nuclear charge, more energy will be given off when we add that electron. So this idea explains the general trend we see for electron affinity. As you go across a period, we get an increase in the electron affinity. We've already talked about beryllium as an exception, neon as an exception, but what about nitrogen in here? We can see that nitrogen doesn't really have an affinity for an electron, and you'll see many different values for this one depending on which textbook you're looking in. But if we look at some electron configurations really quickly, we can try to explain this. So for nitrogen, the electron configuration is 1s2, 2s2, and then 2p3. So if we draw out our orbitals, let's just say this is the 2s orbital, and then these are the 3 2p orbitals. So we'll just do these electrons here. 2 electrons in the 2s orbital, and then we have 3 electrons in the p orbitals. So let's draw those in there. If we try to add an electron to a neutral nitrogen atom, we're adding an electron to one of these orbitals which already has an electron in it. So adding an electron to one of these orbitals, right, the added electron would be repelled by the electron that was in there to start with. And this is the reason that you usually see in textbooks for the fact that this does not follow the trend. Nitrogen doesn't have an affinity for one added electron. So after going through all of that, it's obvious that electron affinity is a little more complicated than ionization energy. And ionization energy we had a pretty clear trend, and it was a little easier to explain why. For electron affinity, going across a period on the periodic table, we see a little bit of a trend, but there are many exceptions to this, and perhaps our explanations are a little bit too simplistic to explain actually what's going on. But across a period, you do see a little bit of a trend. Going down a group is much harder. You see more inconsistencies, and it's not really even worth going over a general trend for that. Electronegativity is probably the most important concept to understand in organic chemistry. We're going to use a definition that Linus Pauling gives in his book, The Nature of the Chemical Bond. So Linus Pauling says that electronegativity refers to the power of an atom in a molecule to attract electrons to itself. So if I look at a molecule, I'm going to compare two atoms in that molecule. I'm going to compare carbon to oxygen in terms of the electronegativity. And to do that, I need to look over here on the right at the organic periodic table, which shows the elements most commonly used in organic chemistry. And then in blue, it gives us the Pauling scale for electronegativity. So Linus Pauling actually calculated electronegativity values for the elements and put them into the table, and that allows us to compare different elements in terms of their electronegativities. For example, we are concerned with carbon, which has an electronegativity value of 2.5, and we're going to compare that to oxygen, which has an electronegativity value of 3.5. So oxygen is more electronegative than carbon, and the definition tells us that if oxygen is more electronegative, oxygen has a greater power to attract electrons to itself than carbon does. And so if you think about the electrons in the covalent bond between carbon and oxygen that are shared, they're shared unequally because oxygen is more electronegative. Oxygen is going to pull those electrons in red closer to itself. And since electrons are negatively charged, the oxygen is going to get a little bit more negative charge. And so it's going to have what we call a partial negative charge on it. So partial negative. Its partial sign is a lowercase Greek letter delta. And so the oxygen is partially negative. It's pulling the electrons in red closer to itself. Another way to show the movement of those electrons in red closer to the oxygen would be this funny arrow here. So the arrow points in the direction of the movement of the electrons in red. So carbon is losing some of those electrons in red. Carbon is losing a little bit of electron density. Carbon is losing a little bit of negative charge. So carbon used to be neutral, but since it's losing a little bit of negative charge, this carbon will end up being partially positive, like that. So the carbon is partially positive, and the oxygen is partially negative. That's a polarized situation, right? You have a little bit of negative charge on one side, a little bit of positive charge on the other side. So it's still a covalent bond, but it's a polarized covalent bond due to the differences in electronegativities between those two atoms. Let's do a few more examples here where we show the differences in electronegativity. So if we're thinking about a molecule that has two carbons in it, and I'm thinking about what happens to the electrons in red, well, for this example, Each carbon has the same value for electronegativity, right? So the carbon on the left has a value of 2.5, the carbon on the right has a value of 2.5. That's a difference in electronegativity of 0, which means that the electrons in red aren't going to move towards one carbon or towards the other carbon. They're going to stay in the middle. They're going to be shared between those two atoms. So this is a covalent bond, and there's no polarity situation created here, since there's no difference in electronegativity. So we call this a nonpolar covalent bond. All right, so this is a nonpolar covalent bond like that. Let's do another example. Let's compare carbon to hydrogen. So if I had a molecule and I have a bond between carbon and hydrogen, and I want to know what happens to the electrons in red between the carbon and the hydrogen, we've seen that carbon has an electronegativity value of 2.5, and we go up here to hydrogen, which has a value of 2.1, and so that's a difference of 0.4. So there is a difference in electronegativity between those two atoms, but it's a very small difference, and so most textbooks would consider the bond between carbon and hydrogen to still be a non-polar covalent bond. All right, let's go ahead and put in the example we did above, right, where we compared the electronegativities of carbon and oxygen. Like that. When we looked up the values, we saw that carbon had an electronegativity value of 2.5 and oxygen had a value of 3.5 for a difference of 1. And that's enough to have a polar covalent bond, right? This is a polar covalent bond between the carbon and the oxygen. So when we think about the electrons in red are pulled closer to the oxygen, giving the oxygen a partial negative charge. And since electron density is moving away from the carbon gets a partial positive charge. And so we can see that if your difference in electronegativity is 1, it's considered to be a polar covalent bond. And if your difference in electronegativity is 0.4, that's considered to be a nonpolar covalent bond. So somewhere in between there must be the difference between nonpolar covalent bond and a polar covalent bond. And most textbooks will tell you approximately somewhere in the 0.5 range. So if the difference in electronegativity is greater than 0.5, you can go ahead and consider it to be mostly a polar covalent bond. If the difference in electronegativity is less than 0.5, we would consider that to be a nonpolar covalent bond. Now, I should point out that we're using the Pauling scale for electronegativity here, and there are several different scales for electronegativity. So these numbers are not absolute. These are more relative differences, and it's the relative difference in electronegativity that we care the most about. Let's do another example. Let's compare oxygen to hydrogen. So let's think about what happens to the electrons between oxygen and hydrogen. So the electrons in red here. All right, so we've already seen the electronegativity values for both of these atoms. Oxygen had a value of 3.5, and hydrogen had a value of 2.1. So that's an electronegativity difference of 1.4. So this is a polar covalent bond. Since oxygen is more electronegative than hydrogen, the electrons in red are going to move closer to the oxygen, so the oxygen is going to get a partial negative charge, and the hydrogen is going to get a partial positive charge like that. All right, let's do carbon and lithium now. So if I go ahead and draw a bond between carbon and lithium, and once again we're concerned with the 2 electrons between carbon and lithium. The electronegativity value for carbon we've seen is 2.5. We need to go back up to our periodic table to find the electronegativity value for lithium. So I go up here and I find lithium in group 1 of my periodic table. It has an electronegativity value of 1. So I go back down here and I go ahead and put in a 1, and so that's a difference in electronegativity of 1.5. So we could consider this to be a polar covalent bond. This time carbon is more electronegative than lithium, so the electrons in red are going to move closer to the carbon atom, and so the carbon is going to have a little bit more electron density than usual, so it's going to be partially negative. And the lithium is losing electron density, so we're going to say that lithium is partially positive. Now here I'm treating this bond as a polar covalent bond, but you'll see in a few minutes that we could also consider this to be an ionic bond, and it just depends on what electronegativity values you're dealing with, what type of chemical reaction that you're working with. So we could consider this to be an ionic bond. Let's go ahead and do an example of a compound that we know for sure is ionic. Sodium chloride, of course, would be the famous example. So to start with, I'm going to pretend like there's a covalent bond between the sodium and the chlorine, right? So I'm going to say there's a covalent bond to start with, and we'll put in our electrons, and we know that this bond consists of 2 electrons like that. Let's look at the differences in electronegativity between sodium and chlorine. All right, so I'm going to go back up here. I'm going to find sodium, which has a value of 0.9, and chlorine, which has a value of 3. So 0.9 for sodium and 3 for chlorine. So sodium's value is 0.9. Chlorine's is 3. That's a large difference in electronegativity. That's a difference of 2.1. And so chlorine is much more electronegative than sodium. And it turns out it's so much more electronegative that it's no longer going to share electrons with sodium. It's going to steal those electrons, right? So when I redraw it here, I'm going to show chlorine being surrounded by 8 electrons. So these 2 electrons in red, let me go ahead and show them, these 2 electrons in red here between the sodium and the chlorine. Since chlorine is so much more electronegative, it's going to attract those 2 electrons in red so strongly that it completely steals them. Right? So those 2 electrons in red are going to be stolen by the chlorine like that. And so the sodium is left over here. And so chlorine has an extra electron, right, which gives it a -1 formal charge. So we're no longer talking about partial charges here. Chlorine gets a full -1 formal charge. Sodium lost an electron, so it ends up with a positive formal charge like that. And so we know this is an ionic bond between these 2 ions, right? So this represents an ionic bond. And so the difference in electronegativity is somewhere between 1.5 and 2.1 between a polar covalent bond and an ionic bond. So most textbooks will see approximately somewhere around 1.7. So if you're higher than 1.7, it's generally considered to be mostly an ionic bond, lower than 1.7 in the polar covalent range. But that doesn't always have to be the case, right? So we'll come back now to the example between carbon and lithium, right? So if we go back up here to carbon and lithium, here we treat it like a polar covalent bond. But sometimes you might want to treat the bond in red as being an ionic bond, right? So let's go ahead and draw a picture of carbon and lithium where we're treating it as an ionic bond. Right? So if carbon is more electronegative than lithium, carbon's going to steal the 2 electrons in red. Right? So I'll go ahead and show the electrons in red have now moved onto the carbon atom. So it's no longer sharing it with the lithium. Carbon has stolen those electrons. And lithium is over here. So lithium lost one of its electrons, giving it a +1 formal charge. Carbon gained an electron, giving it a -1 formal charge. And so here we're treating it like an ionic bond, full formal charges here. And this is useful for some organic chemistry reactions. And so what I'm trying to point out here is, these divisions, 1.7, it's not absolute, it's a relative thing. You could draw the dot structure above, and this would be considered to be correct, right? You could draw it like this, or you could treat it like an ionic bond down here, since it's relatively close to the cutoff. So this is an overview of electronegativity, and even though we've been dealing with numbers in this videos, in future videos we don't care so much about the numbers, we care about the relative differences in electronegativity. So it's important to understand, something as simple as oxygen is more electronegative than carbon, and that's going to help you when you're doing organic chemistry mechanisms.